This video is going to cover canonical correlation and how to analyze multivariate correlation types. So canonical correlation is essentially a correlation with multiple x's and multiple y's. So you really are doing this type of analysis when you want to compare two underlying concepts or latent traits, sometimes they're called, to each other and look at the correlation between the concepts overall, rather than correlating each individual scale you're using to measure these concepts. So it's sort of halfway to structural equation modeling without getting too complicated, and tied also to the idea of how exploratory factor analysis works. So in multiple regression, you can only have one dependent variable, but this lets you have multiple variables assessing that dependent variable. And so the way it works in the background is it creates a regression for each half of the equation. For set 1 and set 2 is how they're listed in the output. But you can kind of informally think about this as IVs and DVs, although the direction of the relationship is usually not predicted. And so we get regression equations on each side that creates a combined predicted score for each person, and then those predicted scores are correlated to get the relationship between your latent concepts. And that's very similar to the way that the variables are combined in MANOVA. And so it creates an overall composite score for each person. And the important thing to remember about CanCore is that you will get several solutions. So there's no one way to combine these variables into their latent traits. There's several different ways. So you will get as many solutions as there are variables on the smaller side. So if you have 4 in set 1 and 5 in set 2, you'll get 4 solutions. So the more variables you have, the more solutions you'll get, but usually only the first couple of solutions will be significant, and that's tested by keeping them orthogonal. So this is similar to exploratory factor analysis if you were to use an orthogonal rotation, and this is where you don't let the variances overlap between solutions. And so that is calculated by using eigenvalues, which is a mathematical representation of the variance that you have. And so you can kind of think about this informally is, let's say you're dishing out dinner to people in plates. And so you put soup in one person's plate and put soup in another person's plate. Well, the soup that I went into the first person's plate cannot go into the second person's plate. So their plates don't overlap. That is orthogonality. And eigenvalues is their sort of a numerical representation of how much soup you put into each plate. Okay? And so it helps you mathematically separate the variance out into distinct groups. Okay? So a couple different things we'll do here. We'll look at how many variates did we find that were significant, and then what do those variates mean? So which variables are the most useful, and how should I interpret the relationships between variates? So there's not a good way to do power here, but we're going to just estimate using correlation, because in a sense this is correlation. We're trying to figure out how well these latent traits correlate with each other. So I'm going to use the default, basically. So t-test with a correlation. I'm going to make it two-tailed because one tail's just cheating. Effect size rho here is how big do you expect the correlation to be. So the standards are 10, 30, and 50. Generally, you're doing canonical correlation if you expect a strong correlation, but I left it at 0.3 just to estimate. Alpha is 0.05, power is 0.8. Calculate. So it says we need 82 people to find a correlation, remembering that generally these sorts of complex designs need lots more people. So this is probably like the lower limit that I tell you to go for, and usually you want to shoot for a lot more, and that just will give you way more power. All right, so some things we have to check for. Larger sample sizes are better. One rule of thumb that I have seen is at least 10 people for each variable. And so if in this data set we have 4, so let me go over here to the end. So what we've done in this study is I have 2 measures of meaning in life or purpose in life. So the PIL, the purpose in life test, and the MLQ, the meaning in life questionnaire. And I'm going to use those to measure meaning. And then I have 2 measures of resiliency, so the brief resiliency scale and the resiliency 14 scale. And so I'm going to correlate meaning and resiliency to talk about how much they really do overlap. So this is a question that people are interested in logotherapy because there are lots of scales that appear to measure the same thing, but we're calling them different names. So we expect the correlations to be quite high. So I would need at least 40 people for this to even really run. It said I would need like 80 some odd people to get this to work. And so I'd want to shoot for larger numbers. Okay. So this is very sensitive to missing data replacement. I don't have any missing data in this example, but you really want to be careful about the type of data replacement you do because it does tend to change things. And then we're going to walk through the traditional assumptions on this example. Okay. All right, so this is a basically double regression analysis, so we have to check for the things that you would expect in a regression. So the first thing I'm going to do is prove to you I don't have any missing data or accuracy errors. So analyze, descriptives, frequencies. I have all the original scores here, but I'm going to use these 4. And so my quick caveat, when you are running a canonical correlation or any type of analysis where you have all of the original questions and you create this total score or subscale score, I would suggest analyzing for outliers separated by scale. So I have 4 scales I'm using here and they each have a different set of questions. I am going to look for outliers right now based on their scores on these 4 totals, but I could have looked at their overall pattern of scores based on the original questions. And so what we've done in some analyses that we've run is when we've had lots of scale data is look at each questionnaire separately and then seeing how many times they were outliers across multiple questionnaires to really get at not just looking at their total score, but the patterns of their total scores and making sure that they didn't get to that total score by just picking 171717 and somebody else picked all 4s and all 4s might be the consistent answer. And so it won't mask people who are doing weird things with the questions by just looking at the total scores. So that's one suggestion I have when you work with this type of data is actually to analyze outliers and normality and stuff by scale and eliminate people who are weird across multiple versions of your scales. But for this analysis, we're going to take the easy route and just look at the 4 total scores, which is what we're going to use. All right, so let me hit statistics here and get the mean, standard deviation. I work with these scales a lot, so I know what they should be. Min and max. Continue. Okay. I forgot to turn off frequency tables, so I got a bunch of extra crap. But if you look at the scores, the overall scores, the PIL is 20 questions, 1 to 7, so 20 to 140 makes sense. The MLQ is 10 questions, 1 to 7, so I don't have anybody at the very, very bottom, but close. The brief resiliency scale is, I've already forgotten, 6 questions. Yeah. 1 to 7. So, should be 6 to 42. So we're within that range. And then the resiliency 14 scale is 14 questions, hence the name, 1 to 7. So we're within the range too. Okay. And what you actually don't see is that when I was making this data for the demo, I actually had miscoded them. And this was the only way I had figured out that I had miscoded which ones were calculated in the total scores. And so it's already fixed for you, but this is still an important step because to get me to this data set, I actually had to do this because I had originally calculated the wrong data. Okay. All right, and you'll notice that the means and standard deviations are very different because the number of questions they have are all different. And so this is where you have to kind of understand the scales you're working with because a 3 standard deviation on the brief resiliency scale is no big deal, and a 20-point standard deviation on the PIL is no big deal. And that's pretty normal. This is what we normally are getting. Okay. All right. As you can see, I do not have any missing data either because I deleted those people already. And so we're going to move on to looking for outliers. These analyses are very sensitive to outliers because it is, at heart, double regression. Okay. So let's create our fake variables to transform compute. We're going to call this random. And click on R, or type R to get random numbers. RB chi-square. 7 has been our favorite number all year. Okay. So that created me a random score, and now I'm going to use a fake regression and look at all 4 of them at once. So this ignores the fact that I'm going to separate them out into meaning and to resiliency, but I just want to know if they have a weird pattern across all of my variables. So let's go analyze, regression, linear. I'm going to put my random variable in the dependence box. All 4 of my set variables in the independence box. We've got plots, z predicted in y, z residual in x, histogram, normal probability plot, continue, and then under options, oops, sorry, it's save. I always do that. So click save and click on Mahalanobis. Mahalanobis here. Continue and OK. That's going to give us a bunch of stuff, but let's go look at the data and look at our Mahalanobis scores. So I'm going to sort that descending to get the biggest scores at the top. You'll notice we have some large ones. I'm going to use my chi-square table. There it is. To come up with the score. Okay, so I have 4 different measured variables. So I'm going to use 4 out here because that's how many I put in the independence box. I'm going to scroll over here and use 0.001. And so it's 1847 is my cutoff score. And you'll notice that gives us 7 outliers. So there are 7 scores, go back out here, that are over 1847. So for the rest of these analyses, I'm going to get rid of them. All right, so outliers are gone. But because I deleted people, I need to rerun my analysis to look at normality, linearity, and all that stuff. So analyze, regression, and linear. Hit OK. You will get Mahalanobis again. Just ignore it. And let's go down here and look at our residual statistics. So this is our multivariate histogram. We have this one dude. There's always that one dude, right? Out here, way past 4. But most of the data is centered over 0. It runs from 2 to 2. So I would say the data is fairly normal. And I don't want to double delete people, so I'm going to leave them in. The linearity plot here is pretty good, especially given the large number of data points we have. If it starts to bend much more, we're going to have a problem. So it's a little non-linear, but I would say it's probably passable. The very last thing is homoscedasticity, because remember this is regression, and this is okay. So essentially, most of the data is between 2 and 2, both directions, or 3 and 3. But the real problem is out here. So yeah, we got that one dude. But this taper here, where it starts to look like a bullet in water, is sort of problematic. Because most of the data is clumped here, which is what you want. And so it's starting to make that megaphone shape. It's not too bad, but if it was to get much more tapered at the end, that's when you would start to worry. All right, so the way you have to run these analyses is the tricky part because you have to do it in syntax. There are a couple of different ways to run this in syntax. We're going to go with the easy one. So you can do this as a MANOVA on its side. But we're going to use the Canonical syntax that is loaded in SPSS. So you either want to download the Canonical syntax from the internet, from our website, or if you search canonical correlation with a space in the middle, .SPS, which is what everyone seems to call SPSS until you work with it a lot, right? So SPS. But if you search canonical correlation.sps, you will find it hidden in one of your folders where SPSS is installed, which is usually under program files, IBM, SPSS 22, etc. Or if you're on a Mac, it's under applications and then all those things. But you want to open that file, or if you search this exact phrase on the internet, you'll find it as well. Let's see, I have that open already, so it should look like this. This window is a syntax editor. And so if you've ever looked at your output for a couple minutes, you'll see there's always this code at the top. Well, that's actually the code that it's running in the background. So you can actually program SPSS and never use the analyze drop-down windows. That's just silly though, because that's the point of having the drop-down windows, the GUI. But if you want to have data, if you want to do something more flexible than the drop-down windows, this is where you go. So a lot of people will use syntax to do things that it will actually mathematically run. It just isn't part of the drop-down point-and-click windows. Okay, and this is one of them. And so somebody has conveniently written us some nice code to run this. Now, it does not automatically remember that you've run this, so you will have to run this code every time you want to do canonical correlation and then close the SPSS. So you can do multiple can cores at once, but once you close SPSS, it's forgotten that this syntax happened. So to get going, what you want to do is highlight everything. So I'm going to use Control A or Command A. Or what you can do is click Run and then All. But I always like to hit the green button, so I'm going to run Selection. Same thing, run the whole file. If that has worked correctly and hasn't freaked out on your computer, what you'll do is you'll get this CanCore SPSS. This version allows long variable names, blah. So that's basically said, I've run it, it's cool, we're down, let's do something else. So that's just getting your computer ready. It's primed to run CanCore now. So the next thing I want to do is I've actually already typed this up, but this little piece here is the syntax for running canonical correlation. I would put this in a separate file so you don't mess up your CanCore file, because otherwise it's going to always look for those variable names. And what you do is you type in the command. So the command that we just ran is CanCore, and then do set1 equals all the variable names that are in set1. They have to match variable view. So let me go back here, go to variable view, and then go back to my syntax here. So they have to match the code names down here. So I've got pill total here, gracious, sorry, and pill total here. Caps lock matters. Okay, so it absolutely has to match or you're going to get some errors. Okay. And then MLQ total, space slash, the next line. Now, it's not technically required to be on the next line, but it does seem to work better. Set2 equals, and then the two, and then the, not two, but two in this example, it could be up to, a zillion. The names of the second set of variables you want to use. Okay. And then at the end, there needs to be a period. The period basically says, and I'm done, stop running. Okay. So it's very simple code here. All you have to do is change out the variable names for this example for your variable names. So I'm going to select everything. Oh, another warning, word of warning. Do not have multiple data sets open. It does get confused, and it will pick the one that it's considered active. And so you want to make sure you just have one of them open so you get the data you're expecting. So highlight all this, click Run. It's going to take a couple minutes. It's going to do a bunch of crazy looking stuff. And then what I'm going to do now is walk you through what all's in the output here. And it's not pretty output, but I can explain what's going on. Okay, so starting at the top, what's going on? The first thing it does is it gives you the correlations between the IVs, or I'm going to call these IVs, but set 1. And so basically it gives me the correlations for one side of the canonical variates. And so that's just my purpose side. And so it tells me that the pill and the MLQ are correlated at 0.52. So it tells me the correlations for my variables on one side. The very next piece down, so that's here, this thing. Very next piece down, it tells me the correlations for the other side, so they're correlated at 0.5. And then this next piece down is it gives me the correlations across sides. So it tells me how correlated are my variables with the other variables on the other side. So basically the pill and the RS14 are very highly correlated, but the least correlation is between the MLQ and the brief resiliency scale. It's only 0.17. And what these three taken together give me is the same thing as a bivariate correlation table in just regular running that in SPSS. Okay, so it's almost easier to look at one of those because you've looked at them a lot. But it does give you the correlations between your measured variables. The next thing down is it gives me the canonical correlates. So this thing. That is where the game is at, so to speak. This is what you're actually interested in. And so this tells me if I combine everything into meaning and everything into purpose, or resiliency, sorry, or whatever your variates are, how correlated are they? So remember, you're going to get multiple answers. So for the first answer, they're correlated at 0.76. If you square that, that's about 58% of the variance. So there's one mathematical equation that tells me that the overlap between meaning and resiliency is about 60%. Okay, and that correlation is 0.76. The second equation, so the second set of variance, is correlated about 0.29. So remember, that's still a medium correlation. If I square that, that's another 9% of the variance. These do not overlap. So this is like 60% of the variance was gone in the first step. So I only have 40% left to work with. So another 9% is accounted for by the second mathematical equation. And so that just tells me the relationship. The relationship between them is positive. So as purpose and meaning go up, resiliency goes up. That's how you'd interpret that. The next thing you get, so let me stack these two next to each other. Let's get a Word document going here. Gracious, I don't even know what that is. There we go. Is here, test so the remaining correlations are 0. That's essentially a question of, do I care if about these variants? Is 60% of the variance a lot, or is that just random chance? Okay, so this tells you if the correlation is greater than 0. So for that first variate, so it's a chi-square analysis. Let's see, for that first variate, it is significant. So 4, and it's 545.45. P-value is less than 0.001. Okay, and I can list R here if I want. So the correlation is 0.76. For my second variate, let's see, so its degrees of freedom is 1, it's 52.36. And that correlation is 0.29. Okay. So they're both significant amounts of variance. So that tells me that they're both important. All right, the next piece down, it tells me what I should interpret. Okay. And so we've got our meaning set, so that's set 1, and our resiliency set, that's set 2. And then overall, ooh, let's make a table. You guys know I love tables if you've been watching my videos. So let's see, meaning, purpose, All right. So let's see. Make this a little bigger here. So I've got meaning here. So meaning and purpose. And then resiliency over here. And then I have variate 1 and variate 2. Variate 1 and variate 2. Okay, and that's the two different solutions that I got. Okay. So what I'm going to list here is the standardized canonical coefficient. Okay, and that is very similar to beta. And so it explains how related each individual variable is to its variate. So you want them to be related to their own variable, because otherwise, why are you using them to measure that variable? So what I'm going to do here is add a little bit more to my table. Oops, not MLQ. So we have brief resiliency scale and resiliency 14 scale. There we go. So I'm creating a table of just like, how related are they to their own variables? Okay. So you could draw a picture to do this, but I'm just going to type it up. Okay. You also get the raw coefficients. So over here we've got standardized coefficients, raw coefficients. You want to use a standardized one. And that means it's comparable across scales that have different scaling. And so since the pill and the MLQ have very different scaling, it will help us to have them in standardized form. So the first one is negative 0.82 and then negative 0.28. For variant number 2 or solution number 2, I got negative 0.83 and 1.14. For resiliency, so I'm going to go from set 1 to set 2 down here. So this stuff, I've got negative 0.91 and negative 0.17. And then 0.70 and negative 1.13. So these are standardized. I can compare them to each other. So looking at them, in the first one, the first variate combination, pill is a much stronger predictor than MLQ. In the second variate combination, MLQ is better because it's bigger. Think absolute values. For resiliency, oh, I did these backwards. Sorry. For the resiliency 14, it's a much better predictor than the brief resiliency scale. For the second variant, that order is reversed. Okay. That doesn't always happen that way. That just happens in this particular set, but you will get different loadings across variants. Unless the scales are totally uncorrelated, and then you might have some trouble because it doesn't know what to do with them because it's hard to combine things into an overall score when they're not correlated with each other. All right. The next thing you're going to get in this output is the canonical loadings. So we're here, and I kind of broke them up. So you get canonical loadings, and then there's cross loadings, canonical loadings, and cross loadings. Let's just talk about what are the canonical loadings. Okay, that is the relationship between that scale and its variant, ignoring that the other one's there. Okay. So the standardized canonical coefficients are like beta. They include the fact that that other variable exists. So just like beta in regression, it is controlling for the fact that the other one's there. So this is pill related to meaning, given the MLQ is still in the equation. The canonical loadings, however, is pill related to the overall variant, and MLQ just doesn't exist. Like we're pretending like it's never even heard the word MLQ before. So this is basically the correlation between that individual scale and the overall meaning scores. And so it sort of pretends like those other variables aren't there. And what we're going to use this for is to determine if these values that I've typed out are important. Because you notice that in all this, you're not getting, like for beta, you get a t-value and you can tell, is it significant? Here you don't. You just get some numbers, and without any context, I can compare them to each other, but I don't know if they're significant. And so what you do is you look at the canonical loadings, and if the loading is greater than 0.3 absolute value, then we're going to say they're significant. Okay, this is very similar to factor analysis. It's a rule of thumb. It's sort of like a cutoff score. So why 0.3? That seems kind of arbitrary. 0.3 is considered a medium correlation. So this is a medium relationship, and we have just decided that that is our sort of lower limit for what we would expect and call important. So medium effect size, essentially. So anything over 0.3, I'm going to star to say that this is a useful variable. So I'm looking at these canonical loadings, and I'm saying anything over 0.3 is useful. So in the first variant, both of them are significantly related to their overall scores. In the second one, only the MLQ is. Okay, because its loading is 0.7 instead, and the pill's loading is 0.2. So that's here. So this negative 0.83 is almost exactly the same as this other one, but in the second variant, it is not important. is essentially what we're saying. So that's why you have to do this. You can't just look at the numbers and go 0.83 is big on both of them. You have to look at the loadings to determine if this number is useful for you. Let's look at the loadings for set 2. Sorry, SPSS is being persnickety. So here, gracious, here, no clicking. And you see that same pattern where it's useful in the first one, both of them are good in the first one, and then in the second one, only the brief resiliency scale is important. And I think essentially what's happening is that the pill and the RS are stronger predictors, much stronger predictors if you look at the values of their overall combined scores. And so since these are totally orthogonal, they're sort of getting all used up in that first analysis. And so in the second analysis, the other variable is really shining through. All right. So that tells me what's important and how they're related. So you kind of have to stop and interpret these here. I'm going to do my best because it's a little odd that they're negative. And so essentially what we're saying is that the pill and the MLQ in this first variant are significantly related to overall meaning, right? Okay. So this is variant 1. Okay. This is the one that explains, like I said, 60% of the variance. And we're saying that the resiliency scores and brief resilience scores are significantly related to overall meaning. However, it's a little odd because it's negative, and I feel like they should both be positive, but they're not. And so essentially what happens is as the pills scores get higher, the overall meaning scores are getting lower, which, if you think about this, doesn't make a whole lot of sense, but they're both negatives. And so as both of them are low scores, okay, so the overall combined scores are low, they're both negative. As the overall combined scores are high, they're both positive. So even though we're getting these two negative relationships, it does create a positive correlation. Because remember, positive correlations are that low scores go with low scores and high scores go with high scores. So in this sense, since both sides are completely negative, it creates a positive correlation. So there is a strong positive correlation between meaning and resiliency, that as meaning goes up, so does resiliency. It's just sort of backwards coded in this analysis. It won't always be that odd. Okay. For variant 2, what we're saying is that the MLQ is meaning, significantly related to meaning. And this one's negative. And then the brief resiliency scale is significantly related to meaning. And again, they're both negative. Which makes the overall correlation positive. And so, oops, I'm sorry, the MLQ is actually positive. Okay. So stronger MLQ scores are related to lower resiliency scores, which doesn't totally make sense until you think about the fact that the MLQ is actually made up of a search for meaning. So if you're searching for meaning, you may not be as resilient than if you found it and you know you have it. And so we've got one positive and one negative, but the correlation between them is overall positive. So as MLQ goes up, the brief resiliency scale is sort of going down because it's contributing more on the lower end. All right, the interpretation is the worst part. The other part that you have to sort of look at is how, if our variables are actually measuring their own variance better than the other variance. So this is called either cross-loadings or redundancy analysis. And so you want to make sure that your variables measure their own variables better than they measure the other variables. And so the cross-loadings here should be compared to the canonical loadings. And so I want to make sure that, like, if you look at pill here is 0.97 and pill here is 0.73, that the scores for the canonical loadings are always larger than the cross loadings. So 0.97 is bigger than 0.7, check. 0.7 is bigger than 0.5, check. Okay, 0.2 is bigger than this one, check. 0.7 is bigger than this one, check. Okay, you want to do that for both sides. Why do you care? Well, essentially what we're saying is that the variable measures its own latent score better than the other one. They're going to be related because that's the point of this analysis, but you don't want your purpose variable to measure resiliency better than purpose because then you've got it on the wrong side. The redundancy analysis gives you that kind of the same information, but more on a global scale when looking at proportion of variance as opposed to just the individual pieces. And you want to make sure that, again, they're measuring their own variance better than the other ones. So canonical variate 1 compared to canonical variate, the cross-loading here. So canonical variate across for set 2 for variate 1. It's kind of confusing. So 0.72 is bigger than 0.4. 0.28 is bigger than 0.02. Same thing down here at the bottom. 68% is better than 39%. 32 is better than 3. So you want to compare them going down to their mates to make sure that the variate, the information explained by its own variate is better than the information explained by the opposite variate. And that's considered a redundancy analysis. If it's measuring the other variate better, you've got them on the wrong side or something, or all your variables are measuring the same thing, essentially. The thing that you got, why your screen went all crazy is because if it runs now, sometimes this won't run like on a school computer when you don't have write access to the files. So you might need to find a computer that you have access to read and write privileges, which means you can save files in the folders that it's looking for, is it gives you their actual score. And so what you can do to see kind of what's going on is correlate these scores. So let's do correlate, analyze, correlate by variate. And let's toss in all these different variables we just got. Hit OK. So what is that doing? Look, set 1, that's meaning for variate 1, is correlated with set 2, that's resiliency for variate 1, at 0.76. So what it does is it creates you new columns in your data set that tell you what those overall combined scores would be, and then correlates them for you. And so remember that these things are orthogonal, so you're going to get zeros out here for these other correlations because they cannot be related. That's the whole point. And then here's the second set of correlations down here. So 0.29 is where we get the second one from. And so it lets you kind of see, like, what is it doing? So this score here in the data is the combined score. So it works out the equation by taking each person's individual scores times their standardized loadings, essentially, and adding them up. And that is like their overall score. So I said the pity about MANOVA, when I was talking about MANOVA in a different video, is that you don't get to see the combined scores. You just are then like, yeah, MANOVA's significant, cool, let's do ANOVA. Here you do get to see the combined scores. And so these are what it thinks meaning is for that participant, and the resiliency is. And so that's why I said this one's a little difficult to interpret because you think as purpose goes up, resiliency goes up. And that's essentially what's happening. It's just that they're all coded negative for some reason. And so basically the relationship is positive because everything is negative and it all cancels out with each other. And so that's what you can use them for other analyses, like if you're wanting these combined scores to predict something else, like maybe depression, that is the score you can use for that. Okay. So to report this stuff, what you want to do is talk about how many variates are there, and what are their correlations, and is that significant? And then interpret the variates and their correlations. And that's what I tried to do with talking about like how PIL is stronger in this one, and MLQ is stronger in this one, and this one's positive and this one's negative. And then show that your variables are appropriate, so they are measuring their own variate better than the other variate. So talk about cross-loadings and the redundancy analyses. And so that is the simple way to run canonical correlation in SPSS.